Hello, Hubblers, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute. And this week we've got another really great hangout planned for you this week. Astronomers using the Hubble Space Telescope have been pointing it at black hole jets in NGC 3862, a galaxy that is very far away and that we will learn a lot more about during the course of this hangout. And so we will be learning about black holes, supermassive black hole jets, as well as colliding material within those jets. But before I get started, let me introduce my co-host, because this week we've got a full gang. We've got everybody here this week. I have with me Dr. Carol Christian. She's the Hubble Space Telescope outreach scientist for the Hubble Space Telescope project from the Institute.
Hello.
Also, hello, Carol.
Hello.
Also with me is Scott Lewis. He's driving the internet. How you feeling, Scott?
Much better than
last week you were out.
I missed you guys.
I missed you guys a lot. We're glad you're back.
We missed you. We were glad we didn't get whatever you had.
Yeah, we're glad you're back.
There's a good reason why we're on opposite sides of the country. The show must go on.
Yeah.
So before I introduce our guests, let me just let you know that we want you to interact with us in this hangout, and you can do that in a variety of ways, which I'm going to have Scott tell you about in just a minute. But first, I want to also remind you that if you have not followed us on Twitter, we are at Hubble Telescope. And you'll be getting you can get all the latest news and information about these hangouts from there. And also subscribe to our YouTube channel, Hubble Site channel, and you can also get notifications from us there. We got a lot of cool stuff on that channel as well. So, Scott, how can people interact with us throughout this hangout?
So the best way to get in touch with us is using the Q&A app, which is on both YouTube and Google+. So as we're broadcasting right now, and if you're watching this later on, you can see at the very bottom that we're answering questions. And if you're watching us live, you can put questions in there. We'll see them up here on our right-hand side. And as we respond to them, we'll put a timestamp in so you can see when we're replying to those specific questions. And also, as Tony said, that we're on Twitter, so I am monitoring both the hashtag you see here, Hubble25, and as Tony's lower third showing is hashtag Hubble Hangout, and so I'm monitoring both of those, and we'll be posting some pictures as we're going on, as well as the links to keep people and keep all you guys involved in the conversation.
All right, thanks, Scott. Now, my favorite way to do it is with the Q&A app, because I have it right here and I can see you guys right away. So that would be the easiest way, and I can interject into the conversation if it's a timely comment. So let's get to today's hangout. Anybody who knows anything about who's been watching these hangouts for any length of time knows that the Hubble Space Telescope has been orbiting above our heads for the last 25 years. And one of the great advantages that gives us to have a telescope up in orbit for so long is that we can use it to periodically go back and look at some things that had looked at before. And that's what the astronomers we have with us today have done. They have looked at a galaxy, I've already said, NGC 3862, which we'll learn a little bit more about. They've looked at it at 4 different instances over the last 20 or so years and have been able to see features in this in a jet coming from a supermassive black hole, which is unbelievably great. I mean, the days of a static universe are clearly over. We can see all kinds of cool things going on. And so with me today is Dr. Eileen Meyer. She's the lead author of the paper. Also with me is Dr. Roland Vandermeerl and Dr. Marcus Georgianopoulos. They have all published a paper which appeared in, I believe it was today's issue of the journal Nature. So welcome, guys, and it's good to have you in our hangout.
Thank you.
Good to be here. Thanks.
All right. Eileen, let me start with you a little bit. I want to talk about black holes first. Now, we've said this before in previous hangouts, but galaxies, not all but most, seem to have something called a supermassive black hole in them. Now, what is a supermassive black hole? Can you describe that for us?
Yes, it's very roughly somewhere between 1 million to 1 billion times the mass of our sun.
That's a pretty big range.
It's a big range, but it's you know, in astronomy we a lot of times deal with order of magnitude differences. So that's sort of the supermassive black hole category. What we call a stellar mass black hole might only be 1 time to 8 to 15 times the mass of our sun. There is a whole range in the middle that's kind of lumped into intermediate mass. So that's sort of the category.
Black hole would be something that might be formed from a very large supergiant explosion or a death of a supergiant star, correct?
Yes,
a very
exactly.
large star.
Exactly.
Now, so these supermassive black holes, these are, as you said, 1 million to 1 billion times larger than the sun, and most galaxies seem to have these. But you know, do you think that? What do you think causes these things to happen? Is there any ideas about why they would get so large? Or do they happen over time? Are they the the coalescing of a lot of other black holes, or any
Very
idea?
possibly, and this is one of those things that nature is weirder than our imaginations. I don't think if you went back to astronomy before we knew about these things, people would have said, "Oh yeah, there's black holes a billion times the mass of our sun." We only, we're trying to understand that mystery. It's one of the things that's still open. So we know that they grow, they get bigger, partly by accreting matter. So they form these big disks of gas and dust that fall into the black holes, so they can grow that way. But we also we know that this is not fast enough, given the lifetime of the universe, to grow these as big as they are. So there must have been some more direct collapse mode of forming the original seeds for these black holes. But it's a big mystery that we're trying to figure out now.
And these jets, the ones that you've been observing and that we'll talk about here in just a little bit, do all black holes have them? And I always thought that when things fell into a black hole, they kind of disappeared. They couldn't come back out again. How come things are coming out of black holes here?
That's a very good question, and it's a bit of an abuse of the language when we say, "Oh, there's jets from black holes." The truth is, this matter never fell in the terms of falling past the event horizon. So it's very close, and it's probably in an accretion disk at first that's kind of sliding in towards the black hole. But something about the disk structure and the black hole structure kicks it out. So it never really falls in the first place. To answer an earlier question, jets from black holes are relatively rare. It's only about maybe 10% of these objects that give us jets.
So only 10% of all the so they would have a jet. So, and would they? So it's directly? Am I right in assuming it's directly related to things that are falling into the black hole at the time? So if nothing is falling in, you don't get a jet.
Broadly speaking, that's the case. So you can starve a jet of fuel, and presumably it will turn off. Now, Marcos would like to add something to that, I think.
Okay, go ahead, Marcos.
Yeah, basically you can starve a black hole. If you don't feed a black hole, a supermassive black hole, you do not have a quasar, these very bright point-like sources in the center of galaxies, but you still have a black hole that is just sitting there, like the one we have in our galactic center.
Right, exactly. I was going to say the one in our galaxy right now is quiet, correct?
So basically, as far as we understand things, every single galaxy has a supermassive black hole, but in most of the galaxies, these black holes are not fed anymore. The period that they were getting food from the galactic neighborhood is over. So they are not fed, and they are not what we would call a quasar, meaning an accreting black hole. And also
so they're the same thing. These jets and quasars are the same thing, right?
Well, you can not really. You can have quasars that do not produce jets, but they still have these very bright accretion disks that we see in the optical and UV and in the X-rays.
Oh, so the difference is the quasar is the radiating accreting disk then from the black hole.
That's right. So you have quasars that have just an accretion disk, and you have quasars that have an accretion disk plus the jets coming out. Now, what makes the difference between these two families? We do not know at this stage. It's not clear what is the difference. And these things look very similar if you look at them in the optical. With a telescope like the Space Telescope, they look pretty similar, those that have jets and those that do not. And it's a field of active research to figure out what makes some of them produce jets and some of them not to produce jets.
Okay, so let's talk about the wavelengths a little bit. Now, this was first discovered, I think, in 90. This jet was first discovered in 38, 62, in 92, I believe, and then it was observed for the first time by Hubble in 94. You said it was visible in optical. What other wavelengths are these things very bright in? And I'm talking about the jets themselves. Who wants to take that one, Eileen?
Well, let me comment just
ahead,
in a general sense what is happening with black holes. So you have something that is very small and very massive sitting in the center of a galaxy, and in fact it's so small that it's a black hole. You have material in the galaxy. Stars have stars, and gas and dust are all things you find in galaxies, and the gas has a tendency to fall into the center. And when you have a lot of gas that you try to squeeze in a very small volume, you get friction. So the gas basically has friction with itself, and it gets very hot. So what happens in all of these cases when there is material falling onto a black hole, you have very hot gas that sits next to it, and that produces radiation and emission that you can see in various wavelengths. So something that's very conspicuous in all wavelengths is X-ray emission, because when you have material that gets about 1,000,000 degrees, its natural wavelengths in which it radiates is X-ray emission.
Okay, and is that the dominant wavelength for this then, or are these jets?
Not for the jets necessarily, but for the accretion disks. So
Right,
you're
the
always
accretion
competing. There's many bright sources going on. So you have the accretion disk, and then you also have the jets, and they have very distinct wavelength distributions. So for the jets, actually another name for sources, black holes with jets, is called radio loud active galaxies. And the reason we call them radio loud is because they produce a lot of radio emission. So, and that's from a process called synchrotron emission. So probably you would say that the dominant emission is radio, in the sense that that's really the easiest way to pick up a jet.
Radio loud. Say it again. Radio loud. What?
Radio loud active galaxies.
Radio loud active galaxies.
Yes, or
they
active
would
galactic nuclei.
not be welcome on a bus, I would imagine. Okay, bad joke. Sorry, John. Bad joke.
But they also give you plenty of optical, X-ray, UV, all the way up to gamma rays, even TeV level emission, which is harder than gamma rays. So they're totally multi-wavelength emitters. So you will get the whole entire spectrum covered in these guys. So if you have, a suite of instruments, which we do, fortunately, as astronomers, you can actually take pictures of these in all kinds of different wavelengths.
Okay, well, thanks for the back. Okay, so that's good. So now with that background, folks, let's talk about a little bit about what these guys have done. So over the years, Hubble has looked at this. We've talked about it before. And Scott, would you mind putting up one of the graphics that shows the jet with the different panels on the side from the different observations when you get a chance? And while he's bringing that up, let me ask you, Eileen, describe for us a little bit about your research and what this paper is trying to show us. And Scott has an image here of some of the observations.
Right. So going back to something you said at the beginning, we're now at the stage where Hubble has been up for more than 20 years taking pictures, which allows us to start aligning these images of the same object up and just seeing what's changed over time. And what we found here in this particular galaxy is that this small jet coming out, it looks here like it's coming out straight in the plane of the sky to the right. But this jet is actually pointed very close to our line of sight. So
okay, so this the panel on the left then is the galaxy basically.
Yes, the galaxy.
Looking from the top, right?
Yeah,
or
you can kind of think of it like that, because you notice this kind of grayish disk in the middle. This is actually presumably a thin dust disk that's orbiting around the black hole itself, and we're seeing that face on like a dinner plate. And then the jet is believed to be almost 90 degrees to this face-on disk. So if that helps you, you can kind of now imagine that this jet is not going to the side; it's actually coming at us, just at a slight angle, so that we can kind of still see it.
See some of the detail in it.
Yeah, because obviously, if it was a 100% in our face, we would just see a dot. So.
Okay, so how far away is this galaxy? Let's get, what are some of the? Tell us a little about the galaxy first, then we'll move to the
So this is a very typical environment to see a jet like this. It's not a particularly powerful jet. It's actually somewhat low power compared to the whole population. So this is what's called a giant elliptical galaxy. So the stars are quite smooth in distribution, and that's why you get this kind of smooth halo of light around the jet. That's very typical. This is. Now, you actually said at the beginning that this is a very far away galaxy, and these are all relative terms. So to an astronomer, this is not far away. It's only about 90 megaparsecs. So
that's far away to me.
That's still the local universe to us. So things haven't changed much.
I know, but I had to. I had to work in the Star Wars thing.
Yes. Yeah. So that's kind of the environment we're in. This is a large galaxy that's
a very old galaxy if it's elliptical, right?
Yeah, so elliptical galaxies, as far as our understanding is right now, have gone through mergers and basically are quite old and relaxed, and have now kind of mixed up their stars into a nice little ball, if you want to think of it like that. So not the beautiful spiral like we live in, but something much different.
So it's and crucially here, it's got enough material near this black hole to be feeding it right now, right?
Yes, that is apparently the case. Of course, it's always good to remind people that we don't have. I mean, Hubble is amazing, but we don't have the resolution to like get all the way down and see in fine detail the accretion disk in almost any of these systems. That's still something that we're working on with instrumentation.
Okay, so Carol, let me ask you a quick question. These panels on the left, is this all the same? Can you put it back up, Scott? Now I'm looking at you.
I see Scott.
Anyway, these panels on the right here, this is all. It says it's all WIFC, the wide field camera, and this one F606 filter. Is this all the same instrument?
Actually, no. So the left is labeled correctly for that image.
That's just for the Galaxy. Sorry.
Yes,
all right.
Thank
you.
Yeah, because that would be impossible for those of you that know that the ACS did not exist in '94.
My confusion.
So the first three of these images were taken with the venerable WIFPIC 2 camera. So that's the first three, and then ACS was the final epic. Yeah. So these are actually mixing different instruments and slightly different filters, although they're, as you can see, that we've scaled them to all be roughly the same wavelength.
Okay. I don't know if it's better to keep with this one or to go to the image that Marcos sent us yesterday. I'm not quite sure which is better. The one with all the orange in it, Scott? That might be a better one. I don't know.
That's a nice one also because it's a bit more zoomed in.
Yeah. So getting to the jet itself, we saw 4 observations there over the course of the past 20 years, where what was being revisited and re-imaged.
I actually have a question, and so I'm going to ask Roland to explain this. So we've been talking about elliptical galaxies, but then we have this funny disky thing in the center. So is a jet or jet-like features in ellipticals a signature that there might be more structure than just smooth elliptical structure, or do we know that there are ellipticals that have structure that have no jets and have no black holes, or how does that work? I mean, I know there's no rule for every elliptical galaxy, but kind of what's the census of different kinds of elliptical galaxies and which ones have black holes and which ones have black holes or jets? I guess.
Well, so it's a pretty confusing picture, and you basically find all kinds of things that are not necessarily correlated with either the type of galaxy or the orientation of the galaxy. The fact that there is a jet is believed to be strongly correlated to rotation of the black hole. So black holes have to form from something, from material, and most material in the universe is rotating. So our Earth goes around the sun, our sun is rotating. So whatever this black hole formed from, it probably had some sense of rotation to it, and that means you end up with a black hole that has a spin axis. And what tends to happen is that material comes in sort of in an accretion disk that is perpendicular to this axis, and through some mechanism that we don't fully understand, that presumably involves magnetic fields, some material gets expelled at very high velocities along that spin axis. And a lot of people had looked into this question, and it appears that the spin axis of the black hole, or the orientation of the jet, is not in any clear way correlated with the orientation of the galaxy, or maybe even the type of the galaxy.
Wow.
Spiral galaxies and elliptical galaxies can both be active, and they can both have jets, and it's not that this very center is all that strongly correlated to the grand design features of the galaxy.
So in this particular galaxy, we have this elliptical galaxy, and then we have this spinning disky thing, and the jet then is somewhat perpendicular to that. So it may be that disky thing is actually a little tilted too, right?
Yes.
Do we know if the elliptical galaxy is rotating in the same way or completely different way, or are there any spectroscopic studies of the galaxy itself to know its rotation?
I don't know for this particular galaxy, but in general, elliptical galaxies tend to be sort of the shape of an ellipse. They tend sort of like a flattened football. They do tend, in general, say 90% of the time, to actually rotate in the sense that you would expect. But some fraction of elliptical galaxies actually rotate more like a cigar, so they're like cigar-shaped and they rotate instead of like a sort of like a frisbee. So there is some variety. Until you do the measurement, you can't really tell. I don't know if it's been measured for this galaxy or not.
Great. No. Great. Thanks. All right. So back to the graphics.
Okay. Yeah. So if we can. Okay. So.
Sorry.
No, that was good.
Real quick before we get to the graphic, I wanted to point out something really funny from Twitter. Because we are having some conversation. This is from Heather Archuleta or Pillanaut. So that she might have a drinking game where they all do a shot when someone says accretion disk, and then we'll hang out.
Oh,
so,
man.
Yes. Okay, then.
I'm drinking coffee this morning, so I'll take more coffee. Or an espresso shot. For that graphic we were at there, which I found, I really like the color in this as well, because you're really able to, and the way that we have it all set up, so you're actually able to see the movements over time.
Okay, so I'll have Eileen describe this to us. These are the observations. There are some features in here. Why don't you describe what we're looking at?
Right, so if we start at the very top image, which is how we first saw this jet back in '94. So now we've zoomed in and we've kind of subtracted off the light from the galaxy just because it makes things stand out a little better. And off to the left, there's a little white cross, might look like a dot to some of you. That's actually where the black hole is, and it's actually very bright at that location. So we also subtracted off the light from the core, this black hole, also so that we could see the jet better. So that's why that left side is kind of dark. So the jet is coming from the left, rather, and moving to the right. And you see 4 knots, and these are creatively labeled A, B, C, D. And
nice.
As you will see, we went back in '96, 2002, 2014, and very obviously the middle knot here, which is knot B, was moving very, very rapidly, and we tracked this speed and we measured it, and we found that it appears to be 7 times the speed of light. Okay.
What do you mean appears to be?
It appears to be because, as we know, I hope all of us have accepted that nothing moves faster than the speed of light. So that means that this is actually an optical illusion. This is something that's due to the Doppler effect. It's kind of analogous to the way sounds get higher pitched when like an ambulance or something is coming towards you. Same sort of thing happens here, because again, remember that this jet is actually pointed almost directly on our line of sight.
Right, there's a big line of sight component here.
And it's moving at something like 98% the speed of light in real speed. And what happens is, as soon as the light leaves one of these blobs as it's traveling, it literally catches up to its own light. So by the time we observe this sequence of events on Earth, the whole time series is sped up, and it looks faster than it really is. So
okay, let's say that again, just really clearly.
Yeah.
This is an effect of the fact that it's coming towards us,
yes.
and it appears to be going faster than the speed of light, but it is not. So okay.
Yes.
98%. This thing. So
the real speed is about 98% the speed of light. Yeah.
So it's not like Back to the Future, and that's what's being spaghettified into this black hole. Nothing like that.
No.
It's just because it's blue shifting towards us, so it appears to be going faster. So it's hard to differentiate with the light that we're observing, or what's going on with that.
Yeah, I mean, basically, you see things happen faster than if you were looking at this at a different angle, say. So let's say that this was in the 90 degrees to us. We would see it moving close to 1c. We would see it at its real speed. So right. It's all dependent on that angle that it makes to the line of sight.
And the acceleration that's causing this, what's causing it to go at these speeds is the rate at which it's falling into the accretion disk and then being ejected back out again, right?
No, but if you find out the answer, that's another Nature paper. So
good. Okay, thank you. I'm just starting.
Can we get on that?
All right. Maybe next hangout. Okay, so there's a really great animation that helps to show us these blobs.
Yes, there's a movie.
So let's move on to that. And while Scott's pulling that up, so these things, there are these knots. I mean, everybody, you've pointed them out already. Are these what do you think's causing that? What do you think's causing those features?
I'll let one of the other answer, because I've been talking for a while.
All right. How about you, Marcus? Let me get you in on that.
Yeah.
Yes. So to make one of these knots, you need to increase the activity of the central source for some time. So imagine you have the black hole producing this outflow and for some time the input on the black hole gets higher. So the black hole is going to dump more material into the jet. Then the black hole is going to go back to its initial state, and this additional material will march forward as an entity that we call a blob.
Yes, that's a technical term, a blob.
That's a technical
Stop it
term.
with the jargon. Stop it with the jargon. I may have to explain that.
Is that an acronym? BLOB?
No, sadly, it's a name.
Okay, so Scott has the animation up now, and here we can kind of see the blobs, as Marcos has dubbed, and has coined that term, used for the first time.
I'll work on an acronym for that right now.
Yeah.
Exactly.
So here we can kind of see that. So one of the blobs, I think you said it was blob B, kind of smashes into what
Yes.
blob?
See, the one just downstream. So it's
The one just to the right of it.
The one just in front of it is actually also what we call superluminal, or faster than light. It's moving at about 2 times the speed of light. But because the other one's faster, it's colliding with it, just like a car wreck. So it's not slowing down, so it runs right into the back of it. So that's what you're seeing happen in the final frame. You kind of see how it becomes one blob and gets bright, and that's the collision in action.
So I know that we've stopped in 2014, and that's the last frame we have of this. But
Yes.
do you think it's going to overtake it, or is it just going to keep pushing the whole mess forward? Is it just going to? Now we have super blob, right?
Yeah,
I'll take credit for that.
Now we're kind of in an uncharted territory, so that's kind of why this was a big result, is we've never seen anything like this before. But we think it's going to take about 30 years of our time for this to evolve and to see exactly what happens. But what should happen, if the theory is correct, is that they should merge and then move downstream with a slightly slower speed, somewhere in between the 2 speeds that they initially had. And then it'll keep moving out. So
this explains why Roland is the mission head for WFIRST, which is a future telescope.
yes, yeah, we need to continue taking pictures.
Yeah, so let me actually point something out that may not be immediately obvious when you look at this. So it's actually true in astronomy that the natural timescale for most things to evolve is very long. So of course, the Earth takes a year to go around the sun, but most things that we look at, other galaxies, for example, are much bigger, and the timescale scale with the size of the system. So typically, most things change only over scales of millions of years, which means that as a human, if we take a picture and we take another picture a decade later, things look exactly identical. So the fact that we're actually looking at something here that actually looks different is actually quite remarkable. And what is particularly remarkable is that it is true that you can see things change, but typically they have to be close by. So most of the measurements like this that have been done are measurements in our own Milky Way. That's been done already, a century ago, but very close to the sun, other stars. You can see them slowly move on the sky. With Hubble, you can do such precise measurements that we've now actually been able to do such measurements where we see stars moving, for example, in our local group. So that's basically still within, 1 million light years from where we are. Now, this thing is actually almost, a few 100 million light years away, which means that the only reason we see something move here is because it's going so fast. It's really going, at almost the speed of light. It appears to be going even faster. That's why we can do this so far away. Typically, anything else that you look at this distance will look just the same if you look at it now or you look at it 500 years from now. So this is actually quite remarkable that this can be done, and it's really only Hubble that allows you to do this at this point, because you need these very sharp images. And as Carol points out, if Hubble were to disappear at some point, and if NASA or other space agencies continue to launch future telescopes with similar sharpness of images, we will be able to continue to follow how this evolves over time, which is really a very exciting prospect.
So how bright is this stuff in the infrared? Because JWST is primarily infrared, and I know WFIRST will be one too. So will this be some follow-up opportunities there, or does it seem to be in the optical and above?
No. I mean, this is synchrotron emission, which you don't have to know exactly how that works, but it's a very broad spectrum. So things change slowly as you change wavelength. So if you have HSC resolution, but in infrared band, it should be fine. There's you can't maybe take that to extremes. You wouldn't want to shift all the way up to X-rays, because then you actually might start probing changes within the jet in terms of where X-ray emitting portions are and where the optical is. But infrared is fine.
Okay, good.
Short answer.
Good. Well, that's good. That'll be some follow-up future observations.
So
And
we
so
came up with the blob analogy.
Oh no.
Oh yeah,
have the-
and I put up on Twitter. So this is is it black hole illuminates ongoing bombardment? Is that what a blob is?
that's actually not bad. That's actually not bad. And for those playing the drinking game, accretion disk. Okay,
Yes.
so Louis Perez, let me just get a comment in here real quick from YouTube. This is relevant to what you were just saying about these the blobs smashing into each other. He's asking, is there fusion going on in these particle collisions? In other words, are they hitting each other with enough force to maybe do some to maybe cause some fusion reactions?
So that's a funny thing, because it's hard to imagine what the environment out there is like. But the densities we're talking about are incredibly low compared to the kind of densities that you need for fusion. So the answer is no, definitely no.
Okay.
But there, it's still a very extreme state of matter, if that's any consolation. So we're still talking about particles, charged particles that have been accelerated to have energies up to a TeV, a tera electron volt. So that's very, very high. We're talking like LHC quantities. So.
Okay. Well, that is a consolation. Thank you, because I only deal in extreme matter at this point. That's all I can think in terms of now. So, okay. So there was another question I wanted to get to on the Q&A app real quick that I have to pull up real fast. Okay, this is from Fubar Gorch. Really?
Yeah. At least it wasn't spelled the way it meant to, so it could be something else.
Gosh.
Is the flow in these jets as a whole characterized? Are they laminar, turbulent? Are there velocity gradients? Does it have a vorticity due to the rotation of the accretion disk? Wow, these are good questions.
These are very good questions.
And this can be studied using observations other than redshift or proper motion. Wow, really good, Fubar Gorch. I appreciate that. Anybody want to take that?
I'll let one of the others talk about that.
Okay, who wants that? So let's start with, we've already talked a little bit about whether they're laminar or not. Marcos was saying that as long as the stream of material going into the black hole is relatively steady, then the stream of the jet will be kind of steady. But if it gets kind of clumpy in any way, falling into the black hole, then you get these clumps going out, or blobs, as we've coined them in this hangout. So this one, I can think you could definitely say it's not a laminar flow, not a smooth flow, right?
No.
That's right. And there's another thing that we are finding is working there, not only in this galaxy, but in many jets. You may have a fast spine in the flow and the slower surrounding shift. So the inner part of the jet is faster than the outer part, and there is a gradient. There is a gradient in velocity as you go from the center of the jet, from the spine of the jet, to the periphery.
Wow.
Mm-hmm.
Yeah, and another thing that's maybe interesting to point out is that this is not actually the first jet for which Eileen has done these measurements. She previously wrote a paper a few years ago with some of the same group of people on another galaxy, which is much closer by, but also has a jet that can be seen. And there we actually found that the jet appears to be wiggling a little. So if you think of it in the analogy of like a garden hose, it's like if you have a garden hose and you hold it still, it'll just spray a straight jet. But if you sort of wiggle it, you'll get something that sort of goes like a helix. Mm-hmm. And we actually found some evidence in that particular galaxy for that. So certainly, a jet isn't necessarily just a simple straight thing. There might be other physics going on that we can actually prove with observations of this kind.
Yeah.
Okay. What about the last part of his question? Can these be studied using observations other than I guess you did other than redshift or proper motion? I guess. These were just basically looking at the blobs themselves, and you used redshift to correct it for the speed, but they weren't really used in the observations themselves, right?
Right,
the
yes.
detection themselves,
Yeah.
right? Okay, good question. That was nice. Okay, so Dan Buddha is asking, also on the Q&A app, is this the first galaxy of this kind? He's talking about NGC 3862 itself. Is this the first elliptical galaxy of this kind?
No, I would say it's incredibly typical. for this class of source. It's very, very often. So that's a small caveat to what Roland said earlier, which is that there is a tendency for some of these kind of wimpy jets, which this one is actually classified as kind of a wimpy jet, to be in these big, massive elliptical galaxies that are highly evolved and a bit older, but not 100%. So that's just, it's a tendency, but not a 100% correlation. But in general, if you find a radio jet that's like this, and then you look in the optical to see what host galaxy is it in, that's a very typical host galaxy.
Okay, good. Good question. Good question, Dan. So, Scott, do you see anything on Twitter other than you inventing acronyms?
Other than me, why would I only do that? There's been a lot. There's been just a lot of really great activity with retweets and putting out there. Brian Magner, which is what's his Twitter handle? Let up. Magnific. He's down with the espresso shots, so it's okay for doing espresso shots. Whenever accretion disk is set on air, so have some more caffeine, everybody.
Yes, absolutely, accretion disk. Okay, so we mentioned you. I think it was I think it was Roland who said that the timescales of this are 30 years or so. Does it make any sense to do any more Hubble observations in the near future, or are there any plans to do that, to look back at this thing?
Yeah.
Does it make sense to wait until some more just to give it some time to evolve?
Surely you are joking.
Well, so I think if you ask any astronomer, would you like more Hubble observing time, they will say
the answer
yes.
is yes.
Nah, I'm trying to cut back on my Hubble time. Actually, I've got a little too addicted to it, so
I've got plenty of data.
Yeah.
But maybe a good thing to point out. Maybe a good thing to point out, because not everyone in the audience may know how this works. But of course, Hubble is a telescope that was built by NASA with collaboration from ESA, the European Space Agency, and pretty much any astronomer on the world can put in a proposal. Once a year there is a call for proposals. Anyone can propose and say, hey, if you give me a few hours or a few days of time on this telescope, I would like to do X. And then once a year there's this set of committees that comes together and picks what they consider the best and most meritorious science. So it's a competitive process. So obviously we'd like to keep following these blobs, and if we get an observation every week, that'd be great. But the bottom line is there's very strong competition. So I think there's a very good case to keep looking at this object. But of course, since the timescale for it to evolve is decades, we'd love to look again next year. There's other kinds of observations we haven't done yet. So far, we've done only straight imaging. You might think about polarimetry, other wavebands, whatever. But we'll have to compete. And given that it evolves over a timescale of decades, it's probably hard to make a case to keep doing it every year for the next 30 years, because that means there's science that's not going to be done.
Yeah.
Yes.
We've actually had hangouts on what it's like to try and
guess what? It was 1 year ago, and so in June the review panel will be back.
Yes.
Looking at the next round. So they're showing up in Baltimore pretty soon.
Yes.
Right.
And we have asked for time to look for to get more observations, and just to explain why we would want to do that. You might say, well, you see that it's colliding. Is it still interesting after that? And the answer is, it is still interesting, because what we're actually seeing is brightening. So we see this not getting brighter, and that means that particles are getting energized. And one of the unknowns in our theories is how efficient that is. So we want to keep tracking it, maybe not every year, every other year, to see how much brighter that knot gets over this 30-year timescale.
And I remembered one thing I wanted to bring up before I go back to this question from Ron Smith on YouTube. But these jets are kind of sculpted by magnetic fields. And do we have a sense of just what these things are they? Well, let me start with a more basic question. Would they originate from just the spin of the black hole itself, because the accretion disk has charged particles in it, or do we know a source for this magnetic field, or how strong it is? Is there anything we know about the magnetic fields of black holes? Or is it just a mystery?
It's somewhere between knowing and a mystery. Marcos is probably a good person to have answer that.
Okay, Marcos.
Yeah.
So what we what we believe right now is that this magnetic field is magnetic field that was carried through with the accretion disk in the black hole. And we have essentially two magnetic fields, one permeating the black hole and the other permeating the accretion disk. So you can think of the magnetic field as a spaghetti structure that is orthogonal or at right angles to the accretion disk. So you have the disk and you have the spaghetti coming out. And this is and now the disk is rotating, so this spaghetti is going to be twisted.
So it's really complicated.
And give us this helical structure we saw in the other radio galaxy that Eileen observed, and it has been seen in a few more cases, a few more sources.
And is it due primarily to charged particles in the accretion disk, or does it come from somewhere else?
No,
because as you know, a charged particle, you move a charge through a medium, you'll get a magnetic field. Is it like that, or is that too simple?
It is, because you can think of the accretion disk as plasma, which is a collection of charged particles, right?
Okay. All right, great. So, but as far as anything else about it, it's still TBD, right? You just got to figure out.
That's right. Yeah.
Right. Okay. So Ron Smith is asking an interesting question. I kind of like to elaborate a little more on this. He's asking if it's an apparent speed. This is referring to the blobs, I guess, and the superluminal apparent speed. How can it catch up and crash into the blob? There's actually two parts of that, right? There's the fact that it's an apparent speed, and then there's the fact that it really is going faster than the blob ahead of it, right?
Yeah. So the 98% number is for the knot that appears to go 7c. I don't know the exact number for the other one, but it's a little slower. And the funny thing is, obviously, if you take this jet and knock it over on its side, you would still catch up to the other one, but it would take much longer, like 300 years for it to evolve. So this whole, remember I told you that one of the effects of this optical illusion is that everything is sped up. We see the whole sequence of events very fast. So it's still moving in real speed faster than the one in front of it. We just sort of, we're seeing everything. It's like putting your video on fast forward. That makes sense.
Yeah, that does. That's a cool effect and a fortunate one for us as well.
Yes.
Louis Perez is also asking on YouTube, is there a relation between the mass of the black hole and the presence of these types of jets?
That's funny because there's a press release for another paper today by Marco Chiabergi that says yes. But, I think that paper came out anyway. But there is a let's say an argument that that's the case. I don't know that it's been 100% established, but.
But let me also add to that we mentioned at the beginning of the Hangout that there's really these two types of black holes that we know exist in the universe. One we call stellar mass black holes, and we know they form from the evolution of a normal star. So a very massive star that at the end of its lifetime will undergo supernova, will become a black hole. And we also know of these black holes that are 1 million or 1 billion times more massive and sit in the centers of galaxies. Now, we do actually know that some stellar mass black holes or stellar mass compact objects do have jets as well. So, while the mass may certainly play a role in how things, appear to us, or how prominent the jet may be, it's certainly not that you can only get a jet if you have a black hole above a certain mass, because we already know that we find them in objects whose mass is different by as much as a factor of 1 billion. Wow, so it plays a role, but it's still a much more complex phenomenon than just the mass. It's not just the mass that's regulating it.
Excellent. That's a great question. Thanks, Louis. I appreciate that. Okay, so I think that's all of our questions that we had. Oh, no, I got more now. Let's see. Let me see here. Dan Buddha is asking on the Q&A app, all the black holes at one time emit jets, or what condition is needed for the black holes to emit jets? And we alluded to that earlier. You need to be feeding it, right? It has to have material falling in before these jets will appear. So that we talked about that earlier on. What does Stephen Hawking have to say about this? Charles Bell is asking. I don't know. He's on in our hangout.
Wait, we can call him up.
Yeah, let's call him up. I don't know.
You got him on speed dial, right, Carol?
Yeah.
Yeah. Sorry, don't know, Charles. But that's well, maybe we'll try to reach him, and maybe he'll be on a future hangout. Okay, so.
I have a question. I know that you've looked at one other example of this, but there are many known examples of this phenomenon, and we just don't know the details of the jets and what they're doing. So it's possible that many of the jets and ellipticals are doing this.
Yes, yeah. So we are only just now able, partly because of the the developments of astrometry is basically the field that allows us to align these images very, very well. So we've only kind of got that set of tools on hand, plus the long lifetimes of Hubble, to really start looking at the local universe jets, as I call them, now. So there's definitely more cases where we want to look, and we think we may see something similar, or we may not. That's, it's pure phenomenology at this point. So we're going to look and see if all the jets do something similar to this, or if this is a really strange outlier. So it's probably expected that we will find more of these.
Another question I had is, do you have any, I mean, this is lots of observing time or whatever, but are there correlations of the brightening in other wavelengths that you've seen? Are you seeing some kind of a phenomenon that produces X-rays that suggests it's associated with this matter creating the blob? Or it's a different phenomenon?
That's a good question. In fact, maybe Marcos could say something about the sort of internal shock theory that we think that this, why we think this is a big result for wider reasons.
Well, the first thing one needs to say is that you do expect this flaring up to be manifested in the optical, in the X-rays, in the infrared.
You would think. Yeah, you would think.
Yeah. So that's one thing. The other thing, the reason that this is very interesting is that this collision of blobs, of components, has been theorized about 30 years ago and has been used a lot in another family of sources called gamma ray bursts. These are stellar phenomena that in the collapse of a stellar system, they form a jet that lasts for a few seconds, and we theorize that the emission we get out of this comes from these colliding components. But this has never been seen, never. And this is the first time we actually see it. We see two components actually colliding. That is honestly the reason this research found its way to Nature.
Yeah, I see. But this is at a massively larger scale.
That's right.
Than the gamma ray burst sources. Yeah. Wow, that's amazing. As you say, the phenomenon sort of occurs at many different scales, not just the scale of supermassive black holes, but all the way down to stellar mass.
That's right.
Okay, let me just get a little clarification from Fubar Gorge. He says, for the record, my nick is the first default variable name. Fubar, yeah, I knew that.
I know that.
Followed by the second, followed by who knows what. Okay, so yes, thank you, Fubar Gorge. I appreciate that. And it's also a really good question you asked. So, that overcomes any strangeness in your handle for sure. Okay, I think that's it for this week. Scott, do you have anything to add? Any quick observations?
The only thing I'm seeing there is Michael Jobin's one about, just think about the barbecue you could have. Like, no, we have spaghetti. Remember? It's a black hole. We only have spaghetti.
No barbecue.
There's no barbecue.
Only spaghetti. No barbecue.
All right, folks. All right, guys. Well, I want to thank you, Eileen and Roland and Marcos. Thank you for joining us. This is excellent work. We look forward to hearing more from you. And Eileen, as you get more information from these jets, you come back and let us know about them?
Absolutely.
All right. Thank you guys for being in our hangout. That's it for this week,
our astronomy, food, and drink channel.
Special shots and spaghetti.
That's right. Accretion disc. Okay. All right. So that's it for this week, folks. Thank you all for watching. Next week we're going to be talking about Pluto.
Yay!
The planet. Of this non-planet are doing very strange, bizarre things. Hubble watched it, looked at it, measured it, and we are going to show you what these moons are doing next week. So we look forward to seeing you again. And on behalf of Carol and Scott, guys, this was another great hangout. Thank you very much. And as always, thank you for watching. And keep, I messed it up. As always, keep looking up.
For accretion discs.
And keep all you guys involved in the conversation.
All right, thanks, Scott. Now, my favorite way to do it is with the Q&A app because I have it right here and I can see you guys right away. So that would be the easiest way, and I can interject into the conversation if it's a timely comment. So let's get to today's hangout. Anybody who knows anything about who's been watching these hangouts for any length of time knows that the Hubble Space Telescope has been orbiting above our heads for the last 25 years. And one of the great advantages that gives us to have a telescope up in orbit for so long is that we can use it to periodically go back and look at some things that had looked at before. And that's what the astronomers we have with us today have done. They have looked at a galaxy, I've already said, NGC 3862, which we'll learn a little bit more about. They've looked at it at 4 different instances over the last 20 or so years and have been able to see features in this in a jet coming from a supermassive black hole, which is unbelievably great. I mean, the days of a static universe are clearly over. We can see all kinds of cool things going on. And so with me today is Dr. Eileen Meyer. She's the lead author of the paper. Also with me is Dr. Roland Vandermeerl and Dr. Marcus Georgianopoulos. They have all published a paper which appeared in, I believe it was today's issue of the journal Nature. So welcome, guys, and it's good to have you in our hangout.
Thank you.
Good to be here.
Thanks.
All right. Eileen, let me start with you a little bit. I want to talk about black holes first. Now, we've said this before in previous hangouts, but galaxies, not all but most, seem to have something called a supermassive black hole in them. Now, what is a supermassive black hole? Can you describe that for us?
Yes, it's very roughly somewhere between 1 million to 1 billion times the mass of our sun. That's
a pretty big range.
It's a big range, but it's in astronomy we a lot of times deal with order of magnitude differences. So that's sort of the supermassive black hole category. What we call a stellar mass black hole might only be 1 time to 8 to 15 times the mass of our sun. There's a whole range in the middle that's kind of lumped into intermediate mass. So that's sort of the category.
Black hole would be something that might be formed from a very large supergiant explosion or a death of a supergiant star, correct?
Yes,
a very
exactly.
large star.
Exactly.
Now, so these supermassive black holes, these are, as you said, 1 million to 1 billion times larger than the sun, and most galaxies seem to have these. But do you think what do you think causes these things to happen? Is there any ideas about why they would get so large? Or do they happen over time? Are they the coalescing of a lot of other black holes? Or any
Very
ideas?
possibly. And this is one of those things that, nature is weirder than our imaginations. I don't think if you went back to astronomy before we knew about these things, people would have said, oh yeah, there's black holes 1 billion times the mass of our sun. We only, we're trying to understand that mystery. It's one of the things that's still open. So we know that they grow, they get bigger, partly by accreting matter, so they form these big disks of gas and dust that fall into the black hole, so they can grow that way. But we also we know that this is not fast enough, given the lifetime of the universe, to grow these as big as they are. So there must have been some more direct collapse mode of forming the original seeds for these black holes. But it's a big mystery that we're trying to figure out.
Hello, Hubblers, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute. And this week we've got another really great hangout planned for you this week. Astronomers using the Hubble Space Telescope have been pointing it at black hole jets in NGC 3862, a galaxy that is very far away and that we will learn a lot more about during the course of this hangout. And so we will be learning about black holes, supermassive black holes, black hole jets, as well as colliding material within those jets. But before I get started, let me introduce my co-host, because this week we've got a full gang. We've got everybody here this week. I have with me Dr. Carol Christian. She's the Hubble Space Telescope outreach scientist for the Hubble Space Telescope project from the Institute.
Hello.
Hello, Carol.
Hello.
Also with me is Scott Lewis. He's driving the internet. How you feeling, Scott?
Much better than last week.
Last week you were out.
I missed you guys.
I missed you guys a lot. We're glad you're back.
We missed you. We were glad we didn't get whatever you had.
Yeah, we're glad you're back.
There's a good reason why we're on opposite sides of the country. The show must go on.
Yeah.
So before I introduce our guests, let me just let you know that we want you to interact with us in this hangout, and you can do that in a variety of ways, which I'm going to have Scott tell you about in just a minute. But first, I want to also remind you that if you have not followed us on Twitter, we are at Hubble Telescope. and you'll be getting you can get all the latest news and information about these Hangouts from there. And also, subscribe to our YouTube channel, Hubble Site channel, and you can also get notifications from us there. We got a lot of cool stuff on that channel as well. So, Scott, how can people interact with us throughout this Hangout?
So the best way to get in touch with us is using the Q&A app, which is on both YouTube and Google+. So as we're broadcasting right now, and if you're watching this later on, you can see at the very bottom that we're answering questions. And if you're watching us live, you can put questions in there. We'll see them up here on our right-hand side. And as we respond to them, we'll put a timestamp in so you can see when we're replying to those specific questions. And also, as Tony said, that we're on Twitter, so I am monitoring both the hashtag you see here, Hubble25, and as Tony's lower third showing is hashtag Hubble Hangout, and so I'm monitoring both of those, and we'll be posting some pictures as we're going on, as well as the links to keep people